Hey everybody, this is Mr. Beckstrom, and today we're going to take a look at section 3.11. This is on related rates, and really this is one of the tougher sections that we have in this class, so it's really important that we take a little bit extra time with this section. It's mainly going to be kind of word problems, and we're really trying to look at real world problems where we're finding instantaneous rates of change for certain variables. And we might have even more than two variables in some of these examples here. And it's going to take a little bit of ingenuity to solve some of these, and really a little bit of patience and trial and error. So without further ado, let's kind of take a look at some of the procedures. So this is really a good set of kind of instructions on doing these. So first we want to read the problem, making a sketch to organize the given information and identify the rates that are given and the rate that's to be determined, and write one or more equations that express the basic relationships among the variables. Introduce rates of change by differentiating the appropriate equations with respect to t. That's really kind of using that implicit differentiation that we've already done. Substitute known values and solve for the desired quantity, and check that units are consistent and the answer is reasonable. For example, does it have the correct sign? All right, so let's take a look at an example and see how we would go about solving this. And I'm going to just go over the first example. If you want to pause it and try to do this on your own, you're welcome to. But these are pretty difficult here. So the first one says the legs of an isosceles right triangle increase in length at a rate of 2 meters per second. And it says at what rate is the area of the triangle changing when the legs are 2 meters long? At what rate is the area of the triangle changing when the hypotenuse is 1 meter long? And at what rate is the length of the hypotenuse changing? All right, so let's see if we can solve this. Okay, so it says read it carefully, and we want to draw some pictures if we can. We want to write down what we know and then write down what we're trying to find. So that's the first thing I'm going to do. So I'm going to write or make an isosceles right triangle. Doesn't have to be perfect, but something like this, where these two sides are going to be equal. So I'll call those both x. All right, and then the hypotenuse I can call y. So here's what we have right here, and let's take a look at this first question. Oh, before we do that, what do we also know? We know that the legs are increasing at a rate of 2 meters per second with respect to time. So we know that the derivative of x, because that's the leg of the right triangle, that's what we associate with leg, with respect to time, so we write that dx over dt is equal to 2 meters per second. So that is our known information there. So the first one here is at what rate is the area of the triangle changing when the legs are 2 meters long? So for this first one, they're giving us that x is equal to 2 meters. X is equal to 2 meters. And we're looking for the rate of change. Remember, that's the instantaneous rate of change, which is the derivative of the area. So we're looking for the derivative of the area, we'll call that capital A, with respect to time. And that's going to be our unknown. All right, so what does this all mean? Once I get all the information down, I need to somehow relate the sides to the area. So what kind of formula would relate the sides to the area? Well, notice that these two lengths here meet at a perpendicular, which means that we could call one of them the length and one of them the height. And if that's the case, we can use the formula that area is equal to 1/2 length times height, right? Or length times height. Now in this case, our length is x and our height is x. So this means that for our triangle here, area is equal to 1/2 x plus x, which is equal to 2x, right? yes. Oh, I'm sorry, x times x, which is equal to x squared, not 2x, x squared. I was adding them. All right, so now this is the area of our triangle here. We've related the side length to the area, which is great because now I need to find the derivative of the area with respect to time and the derivative of the side with respect to time. So that means if I just take the derivative, if I do implicit differentiation on this whole thing with respect to time, then we're going to get the dA over dt, and we're also going to get the dx over dt. So let's see how. Remember, we're taking the derivative with respect to time. So that means any time that we don't, or that we take a derivative of a variable that's not time, we have to add that d, whatever that variable is, over dt. So first thing, the derivative of a is just going to be 1. But since we took something that is not time, we also have to multiply that by dA all over dt. Remember, implicit differentiation is equal to 1/2. And now we're going to take the derivative of x with respect to time. So that's going to give us 2x. And since we just took another thing with the derivative of another variable that is not time, we have to write times dx over dt. So when we do implicit differentiation on this equation here, we're going to get this right there. All right, so this is great because now we can kind of clean this up a little bit, and we can say that dA over dt is equal to 1/2 times 2 is just 1. So that's just going to be x times dx over dt. And look, here's the variable that we want, and here are the two unknowns or knowns that we have. So dA over dt, dA over dt is just going to be equal to x, which is 2 meters, times dx over dt, which is 2 meters, or 2 meters per second squared, or per second. Multiply those together, and we are going to get 4 meters squared per second. And that's our answer for A. All right, so I'm going to leave the rate of change of the leg of the right isosceles triangle because they give that to me in the beginning here. And so for the next one, it says, at what rate is the area of the triangle changing when the hypotenuse is equal to 1 meter long? When the hypotenuse is equal to 1 meter long. So really, there's quite a few ways I can do this. But I did get the equation. D, this is from before. Mouse is messing up again. dA over dt is equal to x times dx over dt. Right? So I have this, but now, and we know that this is equal to 2 here, and we're still trying to solve for this, but instead of the x, I need to get this in terms of y here. So how do I do that? How can I find that out? How can I find some equation that relates both the x's and the y's together? Well, this is a right triangle, so I know that the 2 legs squared are equal to the hypotenuse, right? Pythagorean theorem. So this is 2x squared is equal to y squared. Right? Now, if I take the derivative at this point, I'm also going to get a dy over dt here, and that is pretty much what I'm looking for, right? However, what I really want to do is I want to solve this for x and just plug it in here. If I just solve this for x and plug it in here, let's see what happens. So x squared is equal to y squared over 2. And I'll kind of continue it up here. So take the square root of both sides. So x is equal to, and this is going to be the square root of y squared over 2, and I can also write that as just y over the square root of 2. So I'm taking the square root at the top and the square root at the bottom there. So now I can go back to this one right here and replace that x with y over root 2. So dA over the derivative of the area with respect to time is equal to, instead of x, I'm going to have y over root 2. And this is going to be times dx over dt, which we know is 2 meters per second, times 2 meters per second. All right, and when we multiply all that together, we're going to end up remember, our y, I should have wrote that up here, our hypotenuse is equal to 1 meter. 1 meter, so this is going to be equal to 1 meter over the square root of 2 times 2. So the 2 goes up here, and this is meters per second, meters squared per second there, because we have a meter here and then a meter there. And I know that didn't come out very nice. I'm having a hard time with my mouse. So let me make that a little bit cleaner. And I'll also multiply the top and the bottom by root 2. So the final answer will be root 2 meters squared per second. So that's the rate of change of the hypotenuse of this right, oh my gosh, I can't remember, the isosceles triangle. All right, let's take a look at C here. Okay, so going back here, it says, at what rate is the length of the hypotenuse changing? So going back to this, what do we know? We know the rate of change of the legs, and we're trying to find the rate of change of the hypotenuse. So we don't have area anywhere in this, so we can't use an area formula. So what we want to do is we want to find something that just relates the legs to the hypotenuse, and that's going to be easy. That's the Pythagorean theorem. So we're going to get 2x squared again. 2x squared is equal to y squared, because it's x squared plus x squared is equal to y squared. And what we want to do is we want to be able to use this dx over dt, which we can do by doing implicit differentiation with respect to t on this side. But if I do it to this side as well, I'm going to get 2y times dy over dt. And dy over dt is what I want, because that's going to be the rate of length, the rate of change for the hypotenuse. But the y there means I need to know also the length of the hypotenuse. And it doesn't give me that either in C or in this top one here. So in order to get rid of the y altogether, I need to get the y down to a single y. Because if I take the derivative of a single y, I'm just going to get the 1. And then I don't care about the length of the hypotenuse there. So I'm going to solve for y here. So take the square root of both sides like we did before. So y is equal to, this is going to be just the square root of 2 times x, because it's the square root of this, and I just do them separately there. And I'm going to get a dy over dt here. Hold on. I'm sorry. I got a little bit ahead of myself. And you take the derivative of both sides. So the derivative of y with respect to t is just going to be dy over dt. And then the derivative of the square root of 2 times x with respect to t is just going to be the square root of 2 times dx over dt. And now all we have to do is just replace the dx over dt with that, and then we're going to solve for dy over dt, which is the rate of change of the hypotenuse. So dy over dt is going to be equal to 2 root 2, I'm just plugging in the 2, meters per second. Meters per second. And it's not meters squared, it's just meters. Okay, guys, that is it for that question. Let's take a look at one more. Okay, so here it says a spherical balloon is inflated and its volume increases at a rate of 15 cubic inches per minute. What is the rate of change of its radius when the radius is 10 inches? So go ahead and give this one a try. Kind of read through the procedures, draw some pictures, see how far you can get, and then we'll go over the solution. Alright, so we have a balloon. We have a balloon. The radius here is going to be 10 inches. 10 inches. And we know that the volume, actually we don't know the volume, do we? What we do know is the rate of change of the volume, so that's going to be dV over dt, the derivative of the volume with respect to t. We know that that is 15 cubic inches per minute. Now I could put these units in everywhere like I did last time to come up with the answer, but I do know that the radius here is just the distance, so and the rate of change of a distance is just going to be the unit to the first power. So I know that my answer should be just inches per minute here. So I don't need to really carry all those around unless I want to. So remember, when we're talking about a distance, we use the unit to the first. If we're talking about area, we do the unit to the second power. And if we're talking about volume, like we are here, we talk about the unit to the third power. So I'm going to leave those off in my calculation and just make sure that my last answer is going to be in inches per minute. All right. So I know this. I want to find the rate of change of the radius, so I want dr over dt in my final answer, and that's going to be equal to, we don't know yet, and we also know that the radius is going to be equal to 10 inches. So I'm just going to write 10 inches there. So what formula pulls all of these together? Pulls together the volume and the radius. And well, that's just going to be the volume for the sphere, and the volume for the sphere is equal to 4/3 pi r cubed. And it looks pretty perfect for us right now. It doesn't look like we need to make any substitutions, because when we take the derivative of both sides, I should get a dv over dt over here, which is this information, and over here I should get an r, which is here, and a dr over dt, which is what I'm trying to solve for. And those are my only variables, so we're in good shape here. So when I take the implicit differentiation, derivative of both sides with respect to t, the left side is just going to be dv over dt, and the right side is, I'm going to pull the, remember, all of 4/3 pi is just a constant here. So I'm going to pull the 3 out front here. Oh, that's weird. So I'm going to get 3 times 4/3 times pi times r squared, right? Just reduce the r by 1. And since I just took the derivative of a variable that is not t, I have to also multiply by dr over dt. All right, and that happens to be what I'm solving for there. So cleaning this up a little bit and doing some substitutions, I know that the derivative of the volume with respect to time is equal to 15. I'm not putting all the units in, like I said. And then the 3's cancel out, so I'm just left with 4 pi times the radius, which is 10. So that's 10 squared times, and this is what we're solving for, dr over dt. So dr over dt is going to be equal to the 15 divided by 4 pi times 100, so that's going to be 400 pi. And it looks like both the top and the bottom are divisible by 5, so that's going to give us 3 all over 80 pi. And remember, this is going to be inches per minute. Inches per minute. And that should be our final answer right there. Alright guys, please ask questions if you have them in the forums, and I can do more videos if you need it. Some of these problems are really a lot harder. A lot of times we have to make those crazy substitutions like we did with the triangles. So just take your time. Let me know if you have any questions, and I hope you all have a great rest of your week. Thanks.